All right, good morning. So the next two lectures will be the last part of the course, which is going to be about data and label efficient learning. Since we started with deep networks somewhere in March, we completed CNNs, then autoencoders, then sequence modeling, followed by explainability, and we just had one lecture on robustness, specifically that was concentrating on anomaly detection. But there's a lot more to robustness literature. If this were a signal processing course, every single algorithm you would learn will have something like a sensitivity analysis. You add a small amount of noise, and then you say whether a particular algorithm is good or not. That is essentially what robustness actually is, and anomaly detection is just one part of that. What was part of the training set versus what kind of a test image you're looking at is essentially what anomaly detection was looking for. But there's other kinds of robustness applications as well. In fact, one thing I wanted to cover, which I was not able to, was this idea of adversarial images, which is you add a small amount of noise, imperceptible to the naked eye, but a network which was predicting correctly with a 99% confidence is now going to predict the completely incorrect class with a 99% confidence. So there are these kind of engineered problems that exist within neural networks, which is a very big problem in terms of robustness of the network itself. But we won't be able to get into that much because this is a much more important topic, which is data and label efficient learning. So the first few slides are about logistics. So I'd shown this to you before. I'm not going to go through the logistics part again. We'll get to the introduction and the goal of the lecture quickly right now. So what we'll be discussing today is a couple of methodologies that is going to look into efficient learning. Specifically about data and label. Now, we need to start by asking the question why we need these kind of efficient learning methods. We've already learned about these kind of supervised learning methods where given a large amount of samples, we assume that there is some kind of a ground truth or a label associated with it. We train a network. It can have multiple millions, billions of parameters, learnable parameters, which are your weights and biases. And once you're able to train that network, then you can deploy it in the real world where given a single sample, you'll be able to predict what its class is, or if you're interested in object detection or segmentation, you can get those labels as well. The question that we start off with is, can we always assume that we have enough label data for good performance? So if you are doing the project, one of the things that you would have noticed is that even though there are 16 classes and many of you took a very long time in order to label these classes, it's not enough. The performance that you're noticing, the gains in performance are not as good as you might have hoped. The reason being that in every single class, there's about 400 segments, segmentation masks that you're given, right? But if you look at something like ImageNet dataset, the entire dataset has about 1 million images with about 1,000 class categories. So assuming that it's balanced, that means that there's going to be at least 1,000 images per category, while you only have access to like 400 per class and sometimes even less based on the annotation masks themselves, based on the quality control part. So it's not always easy to obtain these kind of labeled data for good performance. Let's start talking about why that is the case. We'll formalize the answers to that question and ask ourselves why we don't have fully labeled data always. And there's 4 things, which is that expense in terms of both cost and time, requirements of trained experts, data privacy laws, and unreleased datasets. So these are the 4 main reasons why you might not actually have the amount of data that you want in order to train any deep learning algorithm. Let's look at each of these individually. First one is, let's say, the cost. Cost is a very important part of any workflow. If you're in the industry, for instance, it's very important that the amount of money you spend building these algorithms, you'll get it back somehow, right? But data annotation is itself a big market right now. During explainability, I talked about the idea of Amazon Mechanical Turk. This is one way where you yourself will now be able to You'll be able to basically sign up onto Amazon Mechanical Turk, find tasks that some either industry or research university has put up, saying that they want these labels, and you can do the labeling yourself, and you'll be paid money, essentially. And this is a huge market right now. There are multiple companies that are dedicated to only collecting this amount of data, and it's there across the world. It's a billion-dollar industry right now. The market share, so Germany image video annotation tool segment, for instance, extremely large market share in terms of the annotation that is done. So cost is a significant factor in trying to obtain labeled datasets. Next one is the time. And this also is related to the expense itself, except now it's not in terms of the cost. It's in terms of the time required from the human beings who are actually doing the labeling part. So if you look at machine learning workflows in different industries or in different research problems, it takes a large part of that data collection process. Large part of the machine learning workflow is the data collection process. Even in your project that we did in this, like a 3-month class, half of that was spent just for data collection. Phase 1 was about data collection, and then we distributed the data back to you. And you're using that data in order to construct some algorithms, right? So half your project is based on just data collection from all of you, essentially. This was essentially like a crowdsourcing experiment where you were doing data collection, and then you were utilizing it yourself in order to create the project. So just dealing with the data is not easy. Labeling this data is not easy. So you cannot always expect that you'll have a huge amount of data to do these machine learning tasks. This is a real-world example that we published last year in 2023. In this case, this was actually a collaboration with Ford, where we were working on constructing a data set and using it for different algorithms. One of this was actually active learning algorithm, which we'll discuss on Monday. So in this, the goal was to annotate our object detection. For instance, this kind of a 3D bounding box that you see across this car, along with some other data, which is LiDAR data. There was about a large number of sequences within this data set. One of these sequences, this particular sequence, which we are showing an image from, had about 578 frames. So if you think that 1 second has 30 frames, this basically is about like 15 seconds, 15 to 20 seconds. This is a video that was about 15 to 20 seconds, and it took 1 day and 10 hours. In other words, 34 hours for some third-party labelers to actually label this particular sequence. So a 20-second sequence took about 34 hours in order to label properly. In terms of the this kind of 3D object detection, the LiDAR agent interaction. Of course, you're just seeing the 3D bounding boxes here, but there's a little more to it. The LiDAR data points as well as the interaction is not as easy as just labeling, let's say, the bounding box. But the point I'm trying to make here is that it's a very expensive process in terms of the time as well. And in fact, it took about like the data collection process where Ford had to set up these cameras and do it in Michigan, that took about 6 months, 6 to 8 months. And then the data annotation process took another year, basically. So it was almost like a 2-year kind of a project just to release. I think there was about 120 sequences of data. So this is any data sets that you see out there, it's a very difficult process in order to do the collection. And it's basically something that is expensive both in terms of time as well as money. Another important part, so till now we have just discussed about these natural images, natural videos. So even if you were shown this image and asked to label the bounding boxes for the cars, you will be able to do it because you already have knowledge about what a car is, what a pedestrian is, what fire hose is, what trees are in this particular scene. But there are some data where it's not very clear. You need a lot of expertise in order to do some kind of labeling. So in this particular case, let's look on the left-hand side. This is medical data. This is basically your OCT, your optical coherence tomography of your eyes. So when you take these OCT images, you'll be able to see if there's some diseases. For instance, on the left-hand side here are the diseases CNV, DME, drusen, and a normal eye. This is what it looks like. The goal is now to differentiate, let's say, normal eye from all these diseases. So as a layperson, you wouldn't be able to look at this data and say which image belongs to, let's say, the Drusen category or DME or CNV. It's not very easy. Even with, let's say, 5 to 10 minutes of training, it's not easy for you to do this kind of labeling. You need medical professionals or people who are certified to detect these diseases, to understand the biomarkers that exist within this medical data, to tell you that this is Drusen disease or a CNV or DME or so on. Same thing on the right-hand side as well, like geological processes. If you take the Earth's surface, the subsurface images, it's a very important process in trying to detect earthquakes for carbon sequestration and many other applications. But again, if we look at this kind of an image, it's very hard for us to say what exactly this particular image belongs to, or which segment it belongs to. There's multiple segments within the Earth's surface itself, and it's important to label all of them. Sometimes there's faults as well, which complicates the process. And these faults are very important for earthquake monitoring and for other applications as well. So all of this requires like geophysicists to do the interpretation. So we cannot crowdsource these kind of data. So in the wild, you'll see a lot of image datasets out there because you can leverage Amazon Mechanical Turk. But there's not as much medical or this kind of subsurface image data out there because it's very hard to obtain these kind of labeled data. And a very important part is privacy as well. So it almost looks like, based on the previous slides, I'm putting context of privacy here. Contextually, it might look it's like a negative thing, but that's not. Privacy is very important. We have to make sure that the privacy is maintained of the people, especially like in medical data, for instance. It's going to be extremely bad if I tell you who this belongs to, who this image belongs to, and so on. So maintaining that privacy is very important. And there's a lot of guardrails out there, regulations, where how we can and we cannot release data. Which implies that sometimes some of the data cannot be released based on the privacy values. So these are the kind of things that may affect the fact that you might not have enough data to complete a task. This is where the goal now for efficient learning is that can we train a deep network without needing a lot of labels. A lot of labeled data or labels or data. So in this particular lecture, we'll just discuss about the label part. Next lecture, we'll discuss both data and labels combined together with an active learning setting. But for now, the question for us is, can we train a deep network without needing labels, or at least without needing a lot of labels? And the answer till now has been very simple, which is an unsupervised learning algorithm. When you talked about autoencoders, all you did was reconstruct the exact data that you had before. So there was no requirement of any kind of a label. But between the unsupervised learning and fully supervised learning, there are other modalities, other paradigms of learning that exist as well. Self-supervised, weakly supervised, and semi-supervised. What we'll discuss in this particular class is self-supervised learning, which is a newer modality of learning. For the past, I think, 4 or 5 years, there's a lot more work that has been done on self-supervised learning than the other modalities. Maybe we'll have a couple of slides. I'll see if next lecture I can just have a couple of slides on the other two things. But what we'll be learning for the majority is the self-supervised learning. This lecture will be dedicated to just this part, which is self-supervised learning. All right. So what is self-supervised learning? We can answer that question by thinking about how it's different from existing paradigms of learning, or the paradigms of learning that you have learned till now, which is supervised learning and unsupervised learning. In supervised learning, it's very traditional, it's straightforward. You have X and Y together. In other words, you have X, which is your data, and Y, which is your label, both of them together. You train a network F, you get some prediction Y cap, you take a loss between your Y, which is a ground truth that is given to you, and Y cap, which is your prediction. So, and you'll use backpropagation in order to update the weights within this F and construct the well-trained model, which is your F in this case. So supervised learning is pretty straightforward. Unsupervised learning has no access to, you have no access to y. There's no concept of a label. Given an x, you pass it through the network, you get some output which is x cap, and you take a loss between x cap and x itself. This is exactly what we saw in autoencoders, where you're just reconstructing the data that you already have in order to learn some kind of a latent representation. Of course, I'm just representing f here as if it's just an encoder, but think of this as more as a neural network. So f in this case is both an encoder and a decoder, if you're thinking from an autoencoder perspective. Self-supervised learning takes your x and constructs a different label based on that x to construct this different label called z, and uses that in order to learn this loss function. So you're only given x, which is your input features, or features or your input images, let's say, and you're constructing some kind of a pretext task. So we're going to call this task as pretext task in order to find a label z. So you are kind of constructing these labels z, let's say out of nowhere, in order to now train your algorithm as if it were a supervised learning algorithm. So even though you don't have access to z, you imagine that there is a task, a pretext task, and use that in order to construct alternative label, let's say, and use that within your framework to create this kind of a self-supervised learning algorithm. So this is, the P here is a pretext task, and this pretext task generates these pseudo labels, which is given by Z on the right-hand side, that are used to train a network. When I give examples, hopefully it'll be clearer in terms of what I mean here by Z and P. So how is this different from something like an unsupervised learning algorithm? The main difference is the existence of this pretext task. In unsupervised learning algorithm, I have no in-between P over here in order to say that I want to construct a Z or something like that. The existence of pretext task is what makes your self-supervised learning algorithm different from unsupervised. But it's very, if I go back to this slide here, it's closer towards the unsupervised part than it is to something like fully supervised part. If you see the x-axis here requires more supervision. So as and when you go forward or to the right-hand side in this kind of an unsupervised versus self-supervised versus weakly versus semi versus fully supervised, you need more supervision or you need more labels in order to construct this learning paradigms. So again, the difference between unsupervised and self-supervised is the existence of these pretext tasks. So let's go through the process of self-supervision before looking at an example. So in the beginning, we start with identifying these kind of labeled and unlabeled data. So even when we did autoencoders, we got these clusters, let's say when you did the MNIST dataset, right? Having access to one or two labels within the clusters, you'll be able to then determine which cluster belongs to, let's say, number 1, 2, or so on. So we are assuming that, I don't know, we have 1 million data points, but we only have like 5 labels, like 5 full labels during our training process. So we're going to keep the 5 full labels to the side, and we're going to look at the 1 million data points that we have right now. To be very clear, in unsupervised learning, we only assume 1 million images, and we assume 0 labeled images. And in supervised learning, so this is unsupervised. In supervised learning, I assume 1 million images, and I assume 1 million labels, right? In self-supervised learning, it's 1 million images. Let me delete this. SSL, which is self-supervised learning, I assume 1 million images, and I assume like 5 labeled examples. So this is a good way of trying to understand or differentiate between the different paradigms of learning that can exist. So in this case, the unlabeled data have these x1 to xn, and I'm assuming 1 million. I'm taking the unlabeled data x1 to xn. I'm creating some kind of a pretext task. Again, we'll get to what that pretext task is going to be, and I'm going to convert it into these pseudo labels, pseudo labeled data. So that means that every x1 has a z1 associated with it. xn has a zm associated with it. In other words, I have 1 million of these on the left-hand side, and I will have 1 million of these on the right-hand side, which is pseudo labeled data. Now, so at the beginning, when you have this 5 labeled data, currently we are not taking this into consideration. In other words, when we construct these pseudo labels, we really don't care about what the 5 label data already that exists. We don't care about that. So if this label data has, I don't know, class of x1, y1 was, let's say, 72, right? In this case, your z1 can be 3024, and it'll be fine. It doesn't matter. Your y1 need not be the same as z1, even though it's the actual label that is given to you. You have completely imagined this pretext task P and constructed these pseudo label data. So y1 need not be equal to z1. It's basically, it can be anything that can exist, or anything that we have constructed. So once you have this pseudo label data, you now have a very straightforward supervised learning algorithm. You have x1 to xn, and you have z1 to zm. And based on this kind of data, you now pass it through a network, a ResNet, a VGG, a transformer, any kind of an architecture. You'll get zcap as your output. Take a loss function, lz comma zcap, let's say cross entropy loss, and you update your network with this loss. So once you have the pseudo label data, it's a very straightforward supervised learning process where you'll be able to learn your network based on the pseudo labels that exist. So this is the second step. The third step is now we're going to construct like a very small network, G psi, let's say, on top of our pseudo labeled network, our pseudo label learned network, h of theta, based on, let's say, just the 5 elements that I have, 5 label data that I have. So I pass it through h of theta, I construct a G of psi, I get a y cap at the end of it. Now for these 5 images that I have the labels for, the original correct labels for, I create a loss function, and I'll be able to update both G psi and H theta, or in some cases you only update G psi, you don't touch H theta, you freeze that model and keep it in. But essentially what I'm saying is that these kind of H theta, it has let's say 1 billion parameters, while G psi will have a much smaller case, which let me call it as 1 million parameters. So the idea of self-supervised learning is that I can train a very large model based on a pretext task, but then I have to add on a very small model. Now I know I'm saying it's 1 million and I'm saying it's small, but it's more of a comparison, right? It's order of magnitude lesser than the 1 billion parameter model. So I'll be able to train this 1 million model based on a very small subset of images, a label data that we have. So that essentially is what self-supervision is. Let me go through an example, and then we can stop if anyone has questions. So till now, I've just talked about this P, which is our pretext task, as if it's something that we have imagined, as if it's not something that is rigorous enough. But that's not the case. Designing that pretext task is where the entire idea of self-supervision comes into picture. The simplest and the simplest way of thinking about it is this example. I'm given an image, unlabeled image of a particular dog. I don't know it's a dog. I'm just given this one image as if this were an unsupervised learning algorithm. My pretext task is that I'm going to rotate this dog image by 90 degrees, 180 degrees, 270 degrees. So in other words, given this one image, I'll construct these 3 images. Now in your project, if you're using augmentations, PyTorch transforms, then you'll know that this is a very straightforward augmentation that already exists within learning. But what I'm going to do now is I'm going to create a network that will learn the rotation itself. So my pretext task in this case is to rotate the image and learn what that rotation is going to be. So in this case, it's 90, 180, 270, and so on. Right? So the pretext task here is this idea that I can generate pseudo labels via image rotation. Now again, the goal is classification. Given 1,000 classes and given this image, I need to say that this is a dog, but that's not what we are doing right now. Given any image, I'm just going to rotate it 3 times, and then I'm going to create a 4 class network where first class is rotation 0, next class is rotation 90, 180, and 270. So the network is going to learn the fact that this image has been rotated X amount of degrees. So this is what is happening in the second step here. Your ConNet, or any kind of an architecture that you want, is going to create this loss function between Z cap and Z1, and you're going to update it based on the normal supervised learning that we have. Once this is done, we can add a simple linear layer on top of this ConNet. This is something that we generally do where in something called transfer learning, where you take a convolutional neural network architecture. Let's say you take an AlexNet. Everything except the last layer, you're going to keep it. The last layer, which I believe is something like a 2048 cross 1000, or I think it might be 1000 cross 1000. I forget the exact number in AlexNet. But that particular layer, you remove that, replace that with this kind of a simple linear layer, or 2 linear layers or something like that. So currently, if I were to use this kind of analogy here, it'll be a 2048 cross 4. This is what the network would have learned. 4 is the number of classes, which is 0, 90, 180, and 270. What you do in step number 3 is you remove the 2048 cross 4 and append a different layer, which is 2048 cross 1000 in this case. Let's say we are doing it for ImageNet, so it'll be 2048 cross 1000. And I'm going to use the small set of labels that I have. Let's say I have only access to like 5 labels. I'm going to use those 5 labels in order to construct this kind of a 2048 cross 1000 linear layer at the very end. And similar to the normal supervised learning, I'm just going to update. I'm going to create a loss y cap comma y and update the network based on these small set of labels I have. Any questions regarding self-supervision? All right. So the motivation of self-supervised learning is very straightforward. Learning any pretext task will allow network to learn relevant features without needing explicit labels. So when we discussed about autoencoders and the idea of latent representation, the idea was that there is a latent representation, a smaller dimensional subspace, somewhere in a very high dimensional feature space, which where all the features are going to exist. So that was the idea of manifolds we talked about last time, and when we were discussing autoencoders, right? So the goal is that you have this kind of a feature, let's say, of a particular year. So this year is very important, irrespective of whether you're trying to distinguish whether it's a 90-degree, 180-degree image, or if it's a cat or a dog image. So the same set of features you have to learn. It doesn't matter what your task is, you still have to learn the same set of features. So why not construct a pretext task which really does not have anything to do with your original goal, which is classification of this image as a dog, but you still are learning the same set of features. So we already know that the initial layers are going to learn something like edges, something like these kind of edges, colors, and so on. It doesn't matter if this is coming from this task of training for 90, 180, 270, or if it's coming from, or if it's coming for these kind of, how do you say it, the image classification examples that exist. So the idea of me taking these features and transferring them from one task, which in this case from a pretext task, to the original goal, which is classification, is essentially what self-supervised learning algorithms do. So learning features and learning the task of interest does not have to happen at the same time. Your layer 1, layer 2, layer 3, layer 4, everything until this point is basically learning features, let's say. Let's say I'm telling you that there is a differentiation here, that there is a feature learning and then there is a task learning. If that were the case, then feature learning can happen independent of the task. Now, I want to qualify those statements. They are not true. I'm just using them as a motivation. There is nothing called task versus feature learning within deep networks. But initially, it's quite known that it doesn't matter what kind of task you want. The kind of edges you require is usually going to be the same. If it's a generalizable task, it's always going to be the same, in which case it will be a good idea to learn these initial features without needing that task relevant labels, which in this case is going to be a cat, dog, or any of the other 998 classes. You can construct your own classes, you can construct your own pretext task in order to learn your network. So learning pretest tasks will allow network to learn relevant features without needing labels, and general learned features are usable for any target task. Classification, detection, segmentation are some of the things that we have seen across the course of this lectures. So any of those can be constructed based on these pretext tasks. So that's the basic motivation of self-supervision. Any questions before we move on to the different types of pretext tasks? What you saw was just one example of a pretext task. We'll be discussing about 4 of these over the next 30-45 minutes. All right. So, yes. Um, 5 labels is probably an over-exaggeration, under-exaggeration on my part. Let's say 5,000 images. So instead of having 1 million labels, you have access to 5,000 labels. So it's a little bit larger than 5. But the goal is that this kind of a feature is going to be learned in feature number 4, and in layer number 4, and all that the last layer, the fully connected layers, are doing is trying to construct a task relevant combination of these features in order to say which class it is. So you can think of the initial layers as extracting features and the last layer as combining these features in a task dependent way, and that task dependent way is dependent on the 5,000 labels that we have. But the initial extraction of features is independent of the labels themselves. Any kind of an algorithm, even if I want to rotate it by 90, 180, 270, you can see how the ears are rotated, right? So just by looking at the ears, for instance, I can say what kind of a rotation it is. So that means that I need to have access to this features. I need to have access to the ear features in order to say what the rotation is. But let's say I remove the rotation part, or the task part, which is finding the rotation, I'll still have access to these features. And I can say that because this feature exists, it's a dog. It's not there in a cat. So it's going to be a dog. So that combination of features that happens at the very last layer is something that I'm going to retrain. So this fully connected layer, let's say, is going to be retrained with a linear layer, but all the initial convolution layers in terms of extraction of my features is going to remain the same. I'll still have those ears. I now just need to know that cat doesn't have it. That's it. So a smaller number of labels is more than sufficient to train this kind of a smaller linear layer. In self-supervision, we are just trying to differentiate the idea of feature extraction and feature utility, which is combining them to give them a task. All right, so there are a large number of self-supervision algorithms. The best or the easiest way to kind of differentiate them or to categorize them is thinking about different ways of what these pretext tasks are. Transformation prediction, mass prediction, deep clustering, and contrastive learning. So the first one, the pretext task, performs some transformation on data and task models with trying to learn nature of transformation. So in this case, the rotation is one example that we saw. Another example could be something like a different kind of a transformation, which is, let's say, albumentation, where you're changing the color of your this thing. So you're, let's say, saturating this image by quite a lot, saturating this image by 0.5. or 0.7 or 0.9, and then the goal would be to learn that saturation, right? So that is another kind of a pretext task. Another one can be converting all RGB images to grayscale, changing stuff over there within or changing it to LAB color space or YCBCR color space and changing stuff over there. There are many kinds of these transformation predictions that can exist. If you just go to PyTorch transforms library, you'll see that there are a large number of transformations that can exist, and these are all controllable transformation. So as long as there is a controllable transformation, I can learn what that control variable is going to be. In this case, that controllable transformation was rotation, so I know that I can specify 90, 180, 270. I can use that in order to learn my features, right? So any kind of a transformation you can use in order to learn your features. The simplest, of course, is this kind of a rotation, but there can be many other pretext tasks. So anything that has to do with this idea of transformation is going to come under the transformation prediction. The next one is something like a masked supervision. So the goal in this case is to generate pseudo labels via masking. So I'm, let's say, given this image, I will intentionally mask a certain region. I will remove a part of that part of this region and then train this kind of an autoencoder. So the encoder here is my F that or connet or anything. So F was something I used very far back here, right? So I'm trying to learn this kind of F based on a masked region. So I take this image, I take out the small portion, I pass this through the neural network, but then at the very end, what I have is I want just this masked portion to come out. So contextually, I'm trying to learn this. And this is very relevant when we talked about the in NLP as well, where continuous bag of words, I'm given a large number of context features, and now I need to learn the existing word, let's say, which in this case, I've masked this portion, and I want to learn the masked portion given all the surroundings of it. Right? So this is completely, again, unsupervised. So I don't have access to the labels themselves. I don't know what class this image belongs to, but I've just masked a certain portion, and I want my network to learn what that masked portion is going to be. During training, I have access to this. Right? I know that I have myself masked this part, so I can take this masked region, I can put this over here, and I can construct a loss function and update this kind of a module again, this encoder again. So I'll be able to construct this kind of a network based on the mask that I have myself done, which is a pretext task. And once this is done, again, your encoder has now been trained. Your trained encoder, you can put this kind of a linear classifier on top of it, like remove the final layer, put this kind of a task relevant number of labeled layer at the very end, and you'll be able to construct this. Something's missing here. I think this should be y cap. Y cap is your prediction, and y is going to be your outputs. Any question in what mass prediction is going to be? This was very similar to what we saw in word embeddings when we did the sequence modeling. Next one is deep clustering. It's a little bit more straightforward. Deep clustering essentially means that I train some kind of a connet or connet or some kind of autoencoder architecture, and I'm going to construct these kind of pseudo labels based on my latent representation. So the idea is that even though you don't have access to labels, when you learn this kind of a latent representation, similar images kind of fall in the same latent representation space. So that basically means that you can construct a cluster within your latent representation space. That's why we call it deep clustering. So the clustering is not happening. There's no k-means that is happening on the image space or the feature space itself. Rather, it's happening in the embedding space. So this kind of a deep clustering, when you do that, you'll have access to different classes. So again, if you're using ImageNet, let's say you'll have 1,000 classes, but then you don't know that this is from ImageNet dataset, or you don't know what the number of classes are. You can define whatever your k value is, the number of pseudo labels. You can define your k to be 100, 50, 10, or anything. Once you have that, you'll be able to construct this kind of pseudo labels based on the clusters, and then retrain your and train your network, your connet or whatever encoder you're using, and reuse that similarly to before, where once you have your train encoder, you can add another linear layer, construct a loss function, and construct your and get your goal essentially, which is to get the classification network. So this is about deep clustering. The last one, in which we'll spend a little bit more time, is the idea of contrastive learning. So until this point, the novelty of the methods was in constructing the pretext task itself, but once you do that, it was very similar, where you always had this kind of a setup. You had an encoder that was trained by the pretext task. Now you update your model, your overall goal. You construct another linear layer on top of the encoder. Take a loss function, update it to get the results that you want. Contrastive learning is a little bit different, where it's a more of an engineering approach. It actually comes from the idea of hard negative mining that was there back in the 1980s and 90s, but that then has now been co-opted by this literature of contrastive learning, where the goal is even you don't need to actually, let's say, train an encoder in a separate space. You can do both of these two things together. Your encoder and learning the linear layer can in fact be learned together. And the idea and the goal here is that you utilize the fact that you construct batches within your training algorithms, which is going to be different. So every batch, till now, let's say I have a batch of 128. The only reason I've been taking a 128 batch is dependent on my RAM size, like the amount of memory I have in my GPU. It should not exceed a certain amount. Like if I take something like 256 or 512 on ImageNet, it's not going to work well. Your ImageNet network is not going to train very well. So the usual things that we do in ImageNet is 32 or 128 as our batch size. But whenever we take this batch size, we keep it as is, right? We just 128 batch size means that I have a loss function based on image 1, loss function based on image 2, and a loss function based on image 128, L128. All I do is I add all these losses to get a full loss, a total loss, and I backpropagate that loss in a particular batch, in a, let's call it either a mini batch or a batch. And I do this across the entire data set to complete one epoch. So the entire point of the mini batch learning algorithm that we saw in gradient descent was to make it more efficient, that we cannot have a batch gradient descent. That's why we construct these smaller batches in order to train my algorithm. The point is that every single image is treated differently, is treated the same way, L1 plus L2 plus L3. Of course, you can have some kind of a weighted loss function, but still, your goal has always been to add these small losses independently to go get the overall loss. In contrastive learning, it's a little bit different. You construct this positive negative pairs within each batch, and the positive negative pairs is based on the task that you have constructed. So that means that, let's say I have that dog image that was there before. Let's say that there's about 128 images for dog, cats, or any other images that exist within ImageNet. And many of them have now been rotated based on the pretext task that we have. So positive negative pair will depend on that rotation. Any positives is essentially the class along with its augmentation, along with its pretext augmentation, is going to be the positive class. Negative is going to be everything else that exists within a batch. In other words, if I have 128 images in a batch, let's say 5 of those images are coming from the, or maybe I should say 4 of those images are coming from the dog. The rotations of the dog. So there are 128 images, 4 are based on the rotations of the dog. These 4 are going to be the positive samples that exist within my mini batch. And the remaining 124 are going to be the negatives within this mini batch. Once I have this, my loss function, remember, usual loss function is y comma y cap, right? In normal supervised learning, it's y comma y cap. But in this case, we are going to learn this kind of contrastive loss on top of the embeddings. It's called contrastive loss, where the top portion is going to be some similarity measure of my positive pairs, while the denominator is going to be the everything else, positive and negative pairs combined. The similarity of my positive and negative pairs combined within this loss is going to be the contrastive learning approach. So just to make sure we're all on the same page, on the left-hand side, if you see, so these two things, this is just a rotated version, like a horizontally flipped version. Z1 will be equal to Z2, which is going to be different from Z3 and Z4. But if you look at these two things, the transformation that has happened here is basically just a crop. So you've taken a small crop of this particular image, which has been your pretext task. So these two things are now going to be the same, or they're going to be positives to each other, while they're going to be negatives to the cat images that exist. Once that is done, you can now construct this kind of a contrastive loss, where on top it's just a exponent si comma j. Again, you can use any kind of a similarity function, cosine similarity, or other kinds of function. Depending on that, it's literally different papers that can exist. But the idea is the similarity on top, while everything else is going to be there at the bottom within this cost function to train your network. So the idea of pretext task exists within the loss function right now instead of, or within the batches. It's more of an engineering approach rather than constructing a pretext task separately. Any question on contrastive loss, on contrastive learning? So a very famous paper was back in 2020, just 4 years back. SimCLR it's literally called Simple Contrastive Learning Framework, which is a full form of SimCLR. So this paper came out just 4 years back, but contrastive learning has been one of the biggest things that has happened within computer vision. There's a lot of works out there that utilizes contrastive learning and in general self-supervised learning to construct these kind of algorithms. Probably the most famous one right now is NERF, where given just a few angles of a particular image, you'll be able to construct a 3D model. It's a very well constructed method essentially, but it utilizes these ideas of self-supervised learning and contrastive learning. So in this slide, I have detailed the SimCLR framework. Let's go through it a little bit in more detail. So we start by generating similar pairs in a starting batch by augmenting each image, which basically could be any pretext task we want. It could be based on transformation, it could be based on mass prediction, or you could have already gotten the pseudo labels via deep clustering, doesn't matter. You're just creating those pretext, augmenting it by the pseudo labels. You pass image and generate pair into an encoder space, into a lower dimensional representation space, HI and HJ. So the compressed representations further with projection head to generate some kind of embedding. Projection head is something that we saw in the word embedding case, where basically it was that given some kind of a large latent dimensional representation, we construct a smaller dimensional thing, which is Z1 and Zj. We calculate similarity of generated embeddings. We calculate the noise contrastive estimation loss, which is a previous loss that I showed, using cosine similarity on each pair of image. So essentially, when we talk about similarity, cosine similarity was the simplest thing is that we can use, and that was what was used in the SimCLR paper. And we compute loss over all pairs in the batch and take an average, essentially. Again, a very important difference here is that instead of looking at each image separately, in contrastive learning, we take contrast between images. It's positives up top, and it's going to be negatives at the bottom, negatives and positives at the bottom in your denominator. So generally, again, when it first came out, SimCLR was the top 5 accuracy of SimCLR was just south of 70%, while supervised learning was up top here. But since then, there's been a lot of work that has been constructed within the contrastive learning space. Most of these algorithms are contrastive learning algorithms. What you notice is that SimCLR has, in some cases, exceeded the performance of supervised learning as well. And today, even the SAM model that you're using, for instance, was done using self-supervision at scale. So even though I'm calling this lecture as efficient learning, we just utilize this as a technique right now. So even though you might have a billion images, a billion masks to train with, you still do this kind of self-supervision to understand the features themselves, and then follow it up with a supervised learning framework. You'll still use all 1 billion images in both cases, and you'll be able to come up with a very big, very good models. So all large language models that you see are usually trained with self-supervised learning in the start, and then in a supervised framework later on. Again, there's a lot of algorithms out there in terms of contrastive learning. So what usually differentiates them from SimCLR is the way we have constructed our positive and negative pairs. This can be, there's a lot of creative approaches out there on how you can construct your positive and negative pairs, and based on that, you can have different papers within this self-supervised learning and contrastive learning framework. So here I'll just show 2 to 3 examples of how you can construct them. Let's take with fisheye images. This is a very relevant part of the autonomous vehicle industry, where you don't want to use normal cameras. You want to use something like fisheye cameras, the reason being that it has a wider field of view. But then it doesn't look like normal images. So if I zoom in here, the middle portion looks, from a normal perspective, it looks like what an image should look like. But on the left-hand side, if you see the car, there is a huge amount of distortion that can exist within this frame. So that means that you cannot take normal ImageNet images and use them in order to construct these algorithms. You need these kind of fisheye images to construct algorithms. And we've already seen before, it takes a very, very long time in order to label these kind of images. So what we can then do is construct some kind of positive negative pairs that are not based on classes. So you don't need to know that this and this are the same class. You need to know where they're coming from within the image. So if it's coming from here, it's an object from center. Coming from here, object from edge. In other words, this is class 1 and this will be class 2 within our pretext task algorithm. Again, if I'm looking at this from a goal-oriented perspective of classification, both of them are class 1. Right? Each of them is a car. So both of them are supposed to be class 1. But the fact that they're being taken out from different regions within the image makes them different classes. In this case, it's going to be class 1, it's going to be class 2. And now I can use both these classes together in some kind of a weighing scheme. Your L class plus L region class. The region class, again, this is class 1 and class 2. This is the L class here, and this is the region class. And I can now construct a contrastive learning algorithm that is going to do better than if you did not have access to these kind of regions. So again, positive negative regions can be defined in different ways. You can define it based on the square. This can be class 1, this can be class 2, this can be class 3, 4, or you can do it radially, 1, 2, 3, 4. Or grid-wise fashion as well. It doesn't have to be, it can be the top left corner, top, then top right corner. So there can be these kind of 9 classes that can exist where it comes from. So it's all up to you in terms of how you can define these kind of class-based algorithms. Some of you have worked with seismic examples in your project. It's a very notoriously very hard images to work with, essentially. It's very hard to get the kind of results that you're hoping to get. In that case also, you need some kind of a pretext task. Usually what happens is that when you have this kind of full seismic volume, generally this is 100 kilometers by 100 kilometers. These kind of volumes in the subsurface Earth's data that can exist. So these kind of 100 by 100 kilometers, and then depth can be something like, let's say, 25 kilometers. I'm not very sure about what the usual depth is with these things, but the height and width are generally 100 kilometers by 100 kilometers, and the depth, let's say right now, is 25 kilometers. Usually what we do is divide them into volumes. Volume 1, volume 2, volume 3. And again, our goal is to say that this class, this is a single class, this is a single class, and so on. But if we cannot have that as the labels, we can construct these kind of different volumes, volume 0, volume 1, volume n, and then use them as a pretext task, and which basically means that the positive negative pair is this volume number. We can utilize that volume number in order to construct the pretext task, and then go forward with the learning process. The last one is medical images. So in medical images as well, you can use many kinds of auxiliary information that can exist within this pretext task. So again, our goal would be to say if it's DMV, or not DMV, sorry, it's the motor vehicle thing. It's DME was the disease, then CNV or drusen. These are the kind of diseases that can exist within the eyes that you can notice on the OCT images. But if you don't have access to this, you can just take something like patient ID. Again, this is not privacy issue because you're not releasing the names of the patients, you're just releasing some kind of an ID. Or you can use clinical labels. So some people, in fact, if you go to the doctors, you usually are shown these, A, B, C, D, or these letters, and based on them from a certain distance, and based on them, you are given a certain score. I think that score is called BCVA. I forget the full form of what that means, but actually the best corrected visual acuity or accuracy, I think it's acuity. So that is essentially the number that you get based on how many letters you read from a certain distance, and you can use that. Even though that is not anywhere within this image, it is an indicator of how good your vision is going to be. So it's correlated to the main labels that can exist, and you can use that in order to construct your pretext task based on these kind of clinical labels. Any questions in terms of how you can construct pretext task, or what would or would not make sense in this case? So again, I've concentrated quite a bit on images as well, but there are other modalities. In every other modality, you can use this kind of self-supervised learning. As I mentioned before, something like a very simple continuous bag of words within your NLP can be a very nice and a very simple self-supervised method of generating pseudo labels. You can do it for audio processing modules or text models. In any of these cases, you should be able to construct any kind of self-supervised learning. At the end of the day, just generating these kind of pseudo labels is just going to come out to just creativity. You can construct any kind of pseudo labels as long as these pseudo labels are somehow related to your original labels that you know, or at least the features that you can extract between the pseudo labels and the features that you can extract from the main labels. If they are the same or if they're similar, that's it. Then that means that you will have a good self-supervised learning or a contrastive learning algorithm. It doesn't matter which modality it might be coming from. So the last part is more of an aside. So these days, what we have are called foundation models. So the SAM model that many of you are working in terms of the project is one such foundation model, segmentation model, segment anything model. It's a segmentation foundation model that was trained with 1 billion masks, 1 billion high quality masks on 11 million images. Again, most foundation models that are there right now use a self-supervised learning algorithm. And whenever you see the words foundation models, it might seem like it's a very big deal, but it's really not. For instance, before 2019, what used to happen is we used to take algorithms like ResNet and VGG. Again, VGG I think came out in 2014, and ResNet came out in 2015, 2016. So till 2019, we used to take a pre-trained ResNet model, just take out the final fully connected layer, replace it with a new layer, and then fine-tune this entire model. We used to call that transfer learning. We call that transfer learning. But since then, what has happened is that we now move away from VGG ResNet, and for our underlying model, we use these kind of, let's just call them larger models, which are something like BERT, DALI, GPT, Flamingo. These are the different models that exist. And these models are essentially called foundation models. I think it was a term that was captioned in 2021. So yes, so in 2021, the terminology for these base architecture models was called as foundation models. The most important thing within this foundation models is that it's done at scale. So even though the goal of today's lecture was to talk about efficient learning, so given less amount of labels, your goal is to train algorithms. People utilize these kind of algorithms even when they have a large amount of data. Even when you have a billion masks, you really can simply do a supervised learning unit architecture, right? But you don't want to do that, because if you utilize these self-supervised learning algorithms and then do supervised learning algorithms on top of that, you'll get a much better accuracy, or you'll get much better algorithms or networks. So at scale is very important. This here, I've written it as if it is true, but in most cases it is not. Or at least there's not very good evidence that it is not. Scale brings about emergent properties that are common between tasks. The idea of emergent properties is something called causal emergence. It's beyond the scope of this class. Again, all these slides from the last one, these 3 slides are really not for the, you won't find it in exam. So essentially, it's part of causal emergence, or the goal of learning self-supervised learning algorithms at scale is that even though you don't know what task you'll be asked to do later on, you are learning something. So you and when you repurpose the learned things that you have into the task that you actually require, which is classification, let's say, then there is some kind of a causal emergence that might happen. At least that is a hope of these kind of foundation models. But again, it's a debatable question, and it's really not, there's no proof at all that causal emergence has happened or even might happen just based on scale. So right now we have BERT, DALI, GPT, Flamingo. The most important 2 things that have changed the way we learn or we use these kind of deep learning algorithms is because of 2 things. One is the transformer architecture and self-supervision. Now, we didn't go too much deep into transformer architecture, but it's one step above. As I mentioned before, it's one step above the word embedding thing that we saw when we talked about natural language processing architectures, where given something like a simple LSTM RNN framework, we utilize something called self-attention. So what we saw in lectures was the idea of attention, which is cosine similarity, but then we use self-attention, which is different in the transformer architectures, and then we'll also use self-supervision. So that leads us to the last slide, which is the idea of foundation models. So in this paper, I think was the first time when the terminology was used. Actually, I'm not sure about that, but this is the most popular one which popularized the idea of foundation models, or the terminology of foundation models, which is, if you go through the image itself, your data sources can be anything, any kind of sources. It doesn't always have to be, generally we think of cameras, which is our images, right? But it doesn't have to be. It can be some kind of ambient sensors. So essentially you can have a sensor in your fridge, where if you open a fridge, you know that this exists. Or it could be a biomonitoring sensor as well, your heart rate, for instance. And all of these can be combined together in a single architecture. You don't need a separate architecture you don't need an RNN or an LSTM for sequence modeling, let's say, or a CNN for vision tasks. All of these can be done via the same task, which is any kind of sensor data can move into this kind of a foundation model. Data type can be RGB, it can be some kind of depth, your LiDAR data, thermal data, text, radio, audio. Any kind of data modalities can be handled by these kind of foundation models. Again, it's just a simple not a simple one, but it's a transformer architecture. And given that, you should be able to do any kind of tasks. It doesn't matter if it's image recognition, object detection, segmentation, edge detection, and so on. So even today, if you go to ChatGPT and you ask it to do recognition, it will do it. You'll be able to upload an image. You can, the newer versions, internal versions have it can connect to the internet as well, so you can feed it URL links and so on, right? So it will be able to understand images, it'll be able to understand text, it'll be able to answer questions in terms of different data modalities as well. So that is essentially what a foundation model is. All it's doing is utilizing an architecture which is independent of the data source itself. So while we talked about transformers a little bit, it was always from a sequence modeling perspective, but it works with images as well. The way it works with images is that you take an image, a small patch, first sequence, next patch, second sequence, third patch will be next sequence, and so on. So images are now converted into a sequence model perspective, and a transformer will be able to handle it. So then any kind of data source will be handled by these foundation models, and you'll get your output. That is the entire goal of these foundation models, the underlying factors of which is self-supervised learning. All right, so that is the end of lecture for today. We'll have one more lecture for the course next time on Monday. we'll discuss, so today was discussing about label efficient learning, even though at the very end I took the efficiency out and said that we can use it for anything. But next time we'll discuss label and data efficient. So it's not just we have 5,000 labels and 1 million images, but we'll only have 5,000 images and 5,000 labels. So what is a nice way, or what is an intelligent way of selecting these 5,000 images is basically what we'll discuss within the concept of active learning. So we'll do that on Monday. Just as a reminder again, homework is due on Friday, and we won't be granting any kind of extensions because we need to grade it and give it back to you as soon as possible. So even though, just try to make sure that you run your codes and everything on pay size as quickly as possible. Last day might be very difficult in terms of finding the notes. All right, I'll see you on Monday.